For most of maritime history, accident investigations were detective work done in the dark. Investigators had to piece together scattered wreckage and rely on the memories of shaken survivors. When a ship simply sank beneath the waves, the sea kept its secrets. That exact scenario played out on October 1st, 2015. The modern cargo ship Faro battled 100-knot winds and a Category 3 hurricane. Within minutes, her radios went dark. 33 crew members vanished, and the massive steel vessel became nothing more than a missing point on the map. Searchers eventually found the hull sitting upright nearly 3 miles below the surface. But locating the wreckage doesn't explain the choices and mechanical cascading failures that drove a massive modern ship into a deadly storm. By the late 1990s, cargo vessels had become billion-dollar assets. To ensure complete losses could be investigated, the International Maritime Organization mandated Voyage Data Recorders, or VDRs, for most large commercial ships. These recording units are installed as high up as possible, typically mounted on top of the bridge or on a tall mast. If the ship goes under, the unit needs to be clear of the immediate wreckage so recovery teams have a chance to retrieve it. By recording from the ship's systems directly, the VDR provides a secondary record to compare against survivor testimony, providing an objective log of the voyage. Despite being known as a ship's black box, the VDR is actually painted a highly visible neon orange. It is specifically colored to stand out against gray ocean floors and rusted steel. This cross-section diagram shows the physical engineering required to protect the internal memory. Beneath the bright paint is an armored shell made of titanium or hardened steel, built to withstand the crushing hydrostatic pressure found 6,000 meters below sea level. As the diagram highlights here, nested directly inside that metal shell is a ceramic thermal blanket. It insulates the fragile solid-state electronics from shipboard fires exceeding 1,100 degrees Celsius, heat intense enough to melt aluminum. If the capsule breaks away during a sinking, an acoustic beacon automatically wakes up. It begins transmitting a sharp ping once per second, giving deep-water submersibles a precise target to track for up to 30 days. This heavy engineering ensures the capsule physically survives the descent, protecting the specific data streams recorded within. The unit operates as the ship's central nervous system. It is hardwired directly into dozens of onboard instruments, constantly logging data into a protected 48-hour loop. This top-down vector graphic maps out how the VDR tracks navigation. By pulling data from GPS dialyze send a ship's gyro compass, it records exactly which direction the vessel was physically pointing, even if heavy ocean currents were pushing it sideways. Keeping with the graphic, we can see 2 distinct velocity vectors being logged. Speed over ground measures the vessel's movement relative to the Earth, while speed through water measures movement relative to the fluids surrounding the hull. The difference between these numbers dictates the ship's physical maneuverability against the ocean's resistance. Down in the engine room, sensors log the exact RPM of the propeller shaft. By comparing that mechanical output to the engine telegraph on the bridge, investigators can see exactly what the crew intended to do versus what the machinery was physically able to execute. The unit also captures the environmental reality of the voyage. It pulls in weather station readings, logs radar sweeps, and continuous audio from a ring of microphones mounted inside the bridge. Synchronizing these mechanical inputs with the audio recordings creates a highly accurate timeline. Investigators can hear the warning alarms, watch the engine output drop, and track the exact rate of flooding, second by second. Capturing that timeline is entirely dependent on recovering the hardware, and the system does have vulnerabilities. A high-energy explosion can rip the acoustic beacon away from the data core, or a deep underwater canyon can bury the capsule in thick silt, muffling its signal. When it is located, the recovery requires immense precision. Remotely operated vehicles navigate the twisted steel, using mechanical arms to cut a single designated wire harness. The capsule is then winched to the surface and rushed to a static-free lab for extraction. The impact of this data is visible in the 2012 grounding of the Costa Concordia. The VDR tracked the exact second the hull struck the rocks and recorded the delay in the evacuation order. That solid-state memory provided a timeline of facts that helped investigators establish accountability for the disaster. 3 years later, search teams illuminated the El Faro's VDR 15,000 feet down in the Atlantic. The internal memory was perfectly intact. What followed was a massive investigation. Technicians spent 1,100 hours carefully deciphering audio clips, filtering out the roar of the hurricane to understand the crew's communications. The data revealed a navigational sequence. The bridge crew was relying on weather reports that were hours out of date, leading them to steer the ship into the path of the intensifying storm. As the severe winds and waves battered the vessel, it began to list. This angle caused the engines to lose lube oil suction, resulting in a mechanical failure and leaving the ship dead in the water. As the structural flooding overwhelmed the hull, the bridge microphones logged the final reality of the disaster. At 7:39 a.m., the captain gave the order to abandon ship. Recovered data helps naval architects identify failure points and allows bridge procedures to be updated. While some ships are never found, VDRs offer a way to learn from those that are, using the recorded moments of one voyage to help prevent the loss of another.